Welcome to those coming in. We're just getting set up, and there we go. That looks like we're ready to go there. And let me get my screen set up. There we go. I think you should be able to see my screen now. And we can get started. Welcome everyone who's joining us. My name is Jody Peters. I'm the community manager for the Ecological Forecasting Initiative, which we call EFI. And welcome to anyone who's joining us for the first time for this series, and welcome back to those who have joined us in the past. As always, we have the co-host of the seminar series, the ESA Statistical Ecology section co-chairs. We've got Tong Chu, Jeff Dozer, and Grace DiRenzo. And we're excited to have Dr. Max Pichler with us today to share about the CITO R package to build and train deep neural networks. And Max's presentation material is available on the GitHub repository. I've got that linked on the screen, and I'll put that in the Zoom chat after I go through the next few slides. I'm going to start with a short overview of EFI and give some logistics for today's seminar. Then I'll turn it over to Tong, who's going to share about the ESA Stats section and introduce Max. Let's see, so EFI is an international grassroots group, and our goal is to build and support an interdisciplinary community of practice around iterative near-term ecological forecasts. So you can see in this figure, ecological forecasts are a prediction with its associated uncertainty. And these predictions are made about an out-of-sample state of a system. So this could be a future time, a different place in space, or a different context, such as a taxonomic or functional grouping. And the forecasts are created by combining models and data, and this takes place in this iterative learning loop. And so you can see that on the figure in the right. And then the forecasts are used to help develop methods, give more understanding about the system that's being forecasted. It helps to develop general ecological theory, and then forecasts can also help to make decisions. And we think that this way of making forecasts is better than using a groundhog. So for those of you who aren't in the US, today is Groundhog's Day in the US, and the groundhog has predicted 6 more weeks of winter for us. But we think that this is a better way to make predictions and forecasts. If you're interested in ecological forecasting, we've got lots of resources and activities that you're welcome to join and explore on our EFI webpage. You can find a list of ways to get involved in the About section. You can sign up to become an EFI member, or sign up to join our newsletter listserv, which you can see on the right-hand side of the screen. We send out newsletters every 4 to 6 weeks with high-level announcements, and we recently had a new one go out with updates, so that's available. The majority of our activities take place in our working groups and international chapters, and these are open to anyone who's interested in participating. We're really excited that in the last couple of weeks, we've had a new chapter get launched for our Asian partners. And so if you've got collaborators or are in Asia, do check that out. The resources that we create throughout the community are shared through our website, on our YouTube channel, and through GitHub. We also have a Slack group where more of the day-to-day conversations take place. So if you're interested in that, reach out to us at info@ecoforecast.org. And we have a Zotero bibliography, and this is where we keep a list of general ecological forecasting related papers, as well as papers produced through EFI. I wanted to put in a quick plug again for our upcoming conference. We're excited to have the Canadian chapter hosted this year in Toronto, and so we'll be getting together in August. We'd love to have you join us. And we've got a couple of keynote speakers lined up, and we'll have oral and poster presentations, and there'll be workshops to share tutorials and topical training materials. We'll also have a number of working groups that are going to meet the first day of the conference to work on projects, and then we're excited to explore Toronto a bit and have some social activities and time to network. We are accepting abstract and travel scholarship requests through April 15, so keep that date in mind if you're interested. As a community, we value ecological forecasts that support the well-being of society and helps to make decisions, as well as those that advance basic research. And we think that quantifying and communicating uncertainty is important. We value open science and support training and collaboration in an environment that's safe, inclusive, and respectful. And for today, we're recording the presentation and we'll make that available by next Monday with the closed captions reviewed. We're going to use Zoom chat to share links and other logistics from those of us that are helping with the seminar. If you have questions for Max during his presentation, please submit those using Poll Everywhere. And you can get to Poll Everywhere just going to the link that's on the screen and typing in pollev.com/EFI2026. I'll also put that in the Zoom chat as well after this. And then Tong's going to moderate the Q&A at the end of the seminar. And so with that, I'm going to pass it to Tong to tell you about the ESA Stats section and introduce Max.
Thank you so much, Judy, and happy Groundhog's Day, everyone. So the Statistical Ecology section is one of the many sections within the Ecological Society of America, ESA. So our mission is to encourage research in statistics applied to ecological problems. And also we sponsor forums for presentations of advances in statistical ecology, like this one. And also to facilitate communications between statistics and ecology. So if this is a mission that resonates with you, please consider joining the section. So our current officers, including myself from Duke University, Jeff Dozer from NC State, and Grace DiRenzo from USGS, Massachusetts Cooperative Fish and Wildlife Research Units. So our today's speaker is Dr. Max Pichler. He's a postdoc researcher in the Theoretical Ecology Group at the University of Regensburg. And his research focuses on using artificial intelligence, particularly algorithms from deep learning and machine learning, to study ecological systems such as bipartite networks and also biodiversity patterns. So in addition to the cito package, which he's going to talk about today, Max is also developing SGSDM, so an R package for estimating scalable joint species distribution models. So without further ado, Max, please, we're looking forward to your presentation.
Thanks for your introduction. Just give me a second. Okay, can you see my? Okay, perfect. Yeah, so thanks for the introduction, for inviting me to talk about our package cito that we can use to train, but also interpret deep neural networks in there, which we can then use to analyze data and not only to make predictions. So first of all, these deep learning algorithms are on the rise. So I would say that we are in a third wave in this development in statistics. So in the beginning of the last century, we had all these classical statistical tools that were developed. And the second wave was this emergence of classical machine learning algorithms like random forest or Boost regression trees. But also the beginning of these neural networks is in the 40s and 60s. So the first neural networks or how we can train them, actually these ideas emerged in the 40s. However, one limitations of these deep learning algorithms was always that they were very expensive to compute. So they require a lot of computational resources to calculate them. But this has changed in the 2000s with the emergence of graphic cards, so these GPUs, and with the realization that we can use these GPUs to train these deep neural networks very efficiently. So this was basically the beginning of this AI hype in the last 10 years or last 15 years. And why do we want to use deep learning? So there's several reasons. First of all, usually, or from my personal experience, they outperform statistical models when we want to make predictions. So they excel in predictive tasks. And they achieve that by doing some kind of automatic complexity adjustment. So they have different types of inductive biases that help them to automatically adjust their complexity to the data. And they're also very good in modeling nonlinearities like GAMS, but additionally, and this is maybe what they can do better than GAMS, is that they can also model very complex interaction structures between the predictors. And maybe the biggest reason why deep learning is getting so popular is that they have the ability to handle complex data. So we can use them to handle images, but also time series without having to use summary statistics to reduce these complex data into a data format that we can use with the classical algorithms. So there are several frameworks that we can use to implement these models. And these frameworks must be optimized so that we have this GPU support. And these frameworks started to emerge in the 2000s or the 2010s. And there are only a few frameworks we can use. We can use, for example, TensorFlow, which was released by Google or Alphabet together with Keras. And then we have PyTorch, which I would say is currently the winner of these two frameworks. And now, very new since like 2 or 3 years, we have Torch for R. So this is PyTorch just without the Python. So it has a R front end, but the back end is still Torch, which is also used by PyTorch. And the nice thing about Torch for R is that we can use it directly in R without having to use Reticulate, which is a package that we can use to run Python code from R. And Cito is based on Torch for R because with that we can build a library in R package for training deep neural networks within R without using Python. But the problem with these frameworks is that usually they require a lot of, I would call boilerplate code in the sense of that we first have to define a network architecture. And here is a code example for very small neural networks. So it's still we would need a lot of additional code to transform the data because also these frameworks cannot handle data frames or factors or NAs. And then we have also to prepare the data within Torch in a certain way. And then we even have to write or implement our training loop, so the optimization on our own. So we have a lot of boilerplate code. And the history behind Cito is actually that my master's student a few years ago and I were just at some point very annoyed about this fact that we always have to write all this code just to run a small neural network, because at that time we were trying to understand or improve our understanding about how neural networks behave with respect to identifying certain effects. So we wanted to understand the bias variance trade-off better, and we had to fit like hundreds of thousands of these neural networks with different parameters. And we realized that, okay, we have to implement or to write this package here for ourselves. And later on, we realized, okay, maybe it's interesting for more people, so not only for us. And the package is already available on C-Runs. It's 2 years, and we also published it in here in Ecography. So maybe an important question is, so why is it an R package or not Python? And the answer is that ecologists are in the R world. So there's this nice study from 2019 showing that the number of publications that are relying on R packages is increasing to like 60% here. And I would say the reason is that all the good statistical models are only available in R. So I think there's not yet, maybe it's changing, but for example, all these mixed effect models, we can fit them very well in R, but I don't think there is a good Python package for it. And this is another reason that we have these regression packages, and all of these regression packages have a similar interface. They have this formula syntax, and this allows us to switch easily between these regression packages. And this is what we wanted to provide. We wanted to provide us something similar with a similar interface. And with cito, we are trying to provide that. So basically, we wanted to do everything in one function. So in cito, we have this DNN function, which has this formula syntax, so we can exactly specify the response variable, but also the predictors. I have here, by the way, is an example for a species distribution model. So we had here data for elephant distributions in Africa. And I would say it's a classical species distribution model. We have pseudo absences. And then we have here this regression formula where we have the presence or absence of the elephant depending on all bioclim variables. So this point in the formula just means that all predictors should be used here in this regression. And then similar to GLMs or GLMMs, we have the option to set different likelihoods, but in deep learning, we're not really talking about likelihoods because we don't have this idea about the data generating model. So what we use here is a so-called loss function. So it's just a function that is measuring the error, which we then can use to optimize our deep neural networks. Although we can still use real likelihoods here. And we also have implemented in cito several likelihoods that are commonly used in ecology, like the Poisson likelihood or the negative binomial. Then we can also switch easily between the different devices, so the hardware devices, so the CPU, but also if you have an NVIDIA GPU, you can switch to this device. And also since a few months, we also support the Apple device, so the Apple GPU, this Apple silicon chips. They have also now their own GPU that we can use here in cito. What we can also do in cito is that we can bootstrap the model or bootstrap the data. And this allows us then to calculate confidence intervals that we can use then for the predictions, but also for the interpretation. And with this one function, we can fit a neural network. So here on the left side, you see it for this elephant example. So on the left side is what we call the input layer. It's just there you have so many nodes as predictors. So I guess here for the bioclim, it should be like 18 variables. So we have 18 input nodes. And then you have these hidden layers in between. And then on the right side, you have the so-called output layer. In the output layer, you have one or two nodes depending on your response. So for the presence absence and the binomial, we have basically a logit link at the end. So we only need one node. So if we would do, for example, now kind of a species classification where we want to classify data into 10 species, we would have here 10 output nodes. And after training the model or fitting the model, we can make predictions. But this is only the first part with cito because so a common complaint with deep learning is that they are being considered black box models. So they are being criticized for that we don't know what they're learning, so we don't know the effects in our deep neural network. However, that's not true because they're just very complicated functions and actually we can explain them. And especially this field of explainable AI is developing tools that allow us to understand what our model has learned. And this is important because of two reasons. First of all, we want to understand what our model has learned because we see kind of an opportunity there to identify the best predictive patterns in the data. And the second point is that we have to understand how a model makes predictions because we want a reliable model. So we want our model to make the right predictions because of the right reasons. And then we can run, for example, summary functions to get these effects, and I will explain also in a minute what these effects are. But because of this bootstrapping, we can also produce here standard errors for these effects. And then we have also these RLAs, which are accumulated local effect plots. These are just response effect curves. This is the way they are called in species distribution models. And if we compare now a linear regression model to a DNN, for example, here for this iris dataset, for the linear model, we can use this LM function to fit a very simple regression model. We can do the same with cito using this DNN function. And for both, we can then run the summary function. So for the linear model, we will get these regression coefficients with their standard errors. And if we do the same for our deep neural networks, we will get these average conditional effects, which are actually very similar to marginal effects. And these average conditional effects are an approximation of linear effects. So in this sense, so the interpretation is the same. So in this sense, we see it here also, but I will show you this also later in the code. They're very similar to the effects of the linear regression model. And again, we can also get here standard errors for these effects. If the effects are nonlinear, we can, for example, for GLMs, we can use this effects package to get these effect plots. We can do something similar to the deep neural network using these accumulated local effect plots. And here, for example, we see that actually the effects here are quite linear. But the interpretation is very similar to these effect plots. And usually we are also interested in how much variance is explained by predictors. For that, with classical stats, we can run ANOVA. And for cito, or with these deep neural networks, we can calculate the permutation importance or feature importance, which is very similar to the feature importance of the random forests. And the interpretation is also similar to the ANOVA. It just tells us what is the most important predictor in our data set. So you see that the interpretation, or what we can get out of these deep neural networks, is very similar to our statistical models. So for some general features of cito, so we have also many advanced features, but some very fundamental features is that we have these different loss functions, including some well-known or commonly used likelihoods. And we have also the option to provide a custom loss function, which I will not present today because it's an advanced feature. Of course, we can change the architecture, so we can change the number of these hidden layers, but also the size of these hidden layers. And then very importantly, we have several options for regularization, and I will also talk about this later. So we have L1, L2 regularization, but also dropout and early stopping, which are very important features in deep learning. And then, of course, we can change the optimizers, and we can do something like early stopping and use a validation split automatically during the training. And also we realized, and it's not only for unexperienced user, usually these deep neural networks we have problems with the convergence, or it can happen. And what we try to provide some functionalities to help the users to identify issues with the convergence in the training of these deep neural networks. And here the idea of this baseline loss is very important. And then similar to the other regression packages, we support all these standard S3 functions, like a plot function, which will just plot the trained neural network, which is maybe not so exciting. We can, of course, print the model. We can make predictions, and we can run the summary function to get these XAI effects for our neural networks. And also what is very important in deep learning or in machine learning in general is this problem of hyperparameters. So hyperparameters are parameters that control the behavior of these models, but also the optimization. So for example, the learning rate is the step size of the optimizer, and it's one of the most important hyperparameter, and we have to optimize or adjust this hyperparameter to the data. Also, regularization must be adjusted to the data. And here in cito, we are using this tune function, which will tell in cito which hyperparameter should be automatically tuned by cito. So we can just tell cito that, for example, the learning rate should be tuned, the dropout or the lambda. And within this tune function, we can also set the lower and upper boundaries, but we can also give this function a set of possible values that should be tested. And cito will then do the hyperparameter tuning using under a k-fold cross-validation. And because this can be computational very expensive, this can be parallelized. But also, if you have several GPUs, it can be also at the same time parallelized over several GPUs if you have them. And for the uncertainty, I already said it, we can actually get an uncertainty. We can calculate the confidence interval for the predictions, but also for the XAI effects. And we do that currently with bootstrapping, which is, of course, very expensive. So here also we have the option to parallelize it. So for small networks, we can, or it's already worth to parallelize them on CPUs. But for big data, of course, it would be better to parallelize it over using several GPUs, which is also possible. But after the bootstrapping, we can use this final model, which is then an ensemble model to of course to make predictions, but also to get the standard errors. For example, here for the African elephant, we see here the standard errors over the space. And with that, I would switch to the practical introduction. Okay, so cito is on crun, which means you can install it using the install package function. So if you want the development version of cito, you can install it from GitHub, from our GitHub repository. And I will also use here in this example here now the ecodata set, ecodata package, which you have to install from GitHub. And this ecodata package is a package we are developing, which just has some example data sets from Ecology for our courses. So the most important function in cito is the DNN function. And if we look at the hub, we see that there are a lot of arguments, but don't worry, it's not most of them. You won't need most of them. Maybe let's start with the iris data set. So with these deep neural networks, I already said it can be quite tricky to get them to converge. And the first thing I would always do is to scale our data set. So scaling means that we are standardizing and centering our predictors. So if we have, for example, the iris data set, I'm gonna scale the continuous variable in this data set. If I run the summary, we see that now all of them have now a mean of 0. So we can fit now our neural network. And here, for example, let's start with a regression task. So in machine learning, a regression task is that we want to predict a continuous response variable. Example, let's start with sepal width. Then we can use this formula syntax to specify our predictors. And the important thing for you is that you have to decide on this loss function. If we scroll down here in the help, we have here a table of the supported, the loss functions we support. And here we have the third column tells you what, or an example for this loss function. Here we see, for example, for the mean squared error, we can use it for regression, for predicting continuous values. And with that, we are fitting our first neural network with cito. But we also see directly at the first attempt that we have here problems. So the cito is reporting that the training is stopped because the loss is still above the baseline loss. Yeah, and what is happening here is that we have here this baseline loss on the right side, and this is an intercept-only loss. So we are using just the mean value as a very simple model. And the idea is that if we cannot outperform, or if the loss, which tells you how good the neural network is currently during the optimization, and if this loss is not dropping below the baseline loss, that something is wrong with your setup. But we will get to that in a moment. So when you have fit your neural network, maybe let's try it again. Now it's better because I've changed the learning rate, but again, I will explain in a second how we can do this in a systematic way. When we have fitted our neural network, we can, of course, make predictions. And of course, the next step would be that we compare these predictions against our observed values. Yeah. And I already said that we also support these other standard S3 methods. So for example, we can return the coefficients. However, these coefficients are not really telling you anything because these are just the weights of our neural network that was estimated by cito. And we can visualize this neural network with the plot function. So here we have now our neural network. So on the left side, you see that we have two input nodes on the input layer because we have two predictors. And on the right side, we have one output neuron. We can, of course, change the architecture. So if we go to the help function, we see that the default is that we have two hidden layers and each layer has 50 neurons. And we can, of course, change this. So let's say you want to use 3 hidden layers and each with 10 hidden neurons. And if we plot our neural network again, we see that we have now 3 of these hidden layers. But honestly, I would recommend that you stick to this default we have in cito. I will show you also in a minute that we, in theory, we could also tune and this architecture, so the number of the hidden layers and also the size of the hidden layers, these are also hyperparameters. However, in reality, also research in deep learning found it very challenging to find a general rule how to set up these architectures. And of course, you can also save the neural networks. I mean, this seems to be obvious, but actually with these frameworks like Torch4R or PyTorch, it's not so easy to save these models to your disk. So yeah, this was also something we had to find a way to easily save these models from R. So when we have fitted our neural network, I showed you that we also want to understand how our neural network is making the predictions, or we just want to get out these effects, so to understand what are the best predictive patterns. Let's fit this model from here again. And additionally, I will fit now also a linear model just to compare the effects. So if we run here now the coefficient function on our linear model, we will get these effect estimates here. And if we run the ANOVA, we'll see that petal length is explaining more variance than sepal length. And we can compare these two outputs now to our neural network. So we're going to run also here the summary function. Then first we have here this feature importance. So this is the permutation importance. And interpolation again is similar to the ANOVA outputs. We see that petal length has a higher importance, so explaining more variance than sepal length. And if we look at the effects, so again, these average conditional effects are an approximation of linear effects. We see that sepal length has a positive effect and petal length has a negative effect. And maybe let's compare this to these two effects here from the linear model. Here also we see that sepal length has a positive effect and petal length has a negative effect. And you see that these effects are very similar. Here, this last row is the standard deviation of these conditional effects, and this corresponds to the linearity of these effects. However, as a spoiler, we're gonna remove here this third row in the upcoming CRAN release, so maybe ignore it for now. So of course, we also want to get confidence intervals for these outputs here. For that, we gonna change here this call. We're gonna turn on bootstrap. So we want 20 bootstrap samples. And I'm also, just to demonstrate that we can do it, I'm gonna parallelize this here on 5 CPU cores. But for these small models, it wouldn't be necessary to parallelize it. So we can run a summary again. Just gonna change here the number of permutations that are used in this feature importance. You can ignore it just to speed things up. And now we see that we have these tables, again, these tables, but we have now also the standard errors here for the feature importance, but also for the average conditional effects. So the problem with these average conditional effects is that they are an approximation of linear effects. And if we have now non-linear effects, of course, they are basically kind of misconception, or they're misleading. And to understand or to get an understanding about the nonlinear effects, what we can do is use these ALE, which stands for accumulated local effects. And these ALEs are very similar to partial dependency plots. And we get these effect response curves from these accumulated local effect plots. But here we see that the effects that were learned by our deep neural network are quite linear. And the interpretation is very similar to these all effect plots from the effects package. We see how the response is changing with the values of the two predictors. Okay, so maybe another example for a different loss function. So the classical analysis of this iris data set is that we want to predict the species. So if we look at this data set, we see that we have something went wrong with this data set here. Let's just use the original data set. So we have here the species column, which is telling us which of the observations belong to which species. And now we want to build a classifier that is trained to predict which of these values belong to which species. So then species will be the response. And then we're going to use, for example, these two predictors. And now we have to change the loss function because this is now not a regression task anymore. This is now what we call in machine learning. This is a classification task. And if we scroll to our table, that for example, here we see that we can use the softmax loss function for multi-class species classification. I'm going to switch here the loss function to softmax. So on the right side, again, we see how the loss, by the way, the epochs are just the number of optimization or the number of the iterations for in the optimization. So we see here that the loss is decreasing and it's below the baseline loss, which is good. And after 100 epochs, we have our final model. We can make predictions with this model. And similar to the GLMs, we see that we get here these values, and actually these values, if we don't change anything in the predict function, these values will be on a scale of the linear predictor. So here we also have a link function. And what we actually want we actually want probabilities for these three classes. So we have to change here the type to response to get the predictions on the scale of the response. And then we get here probabilities for all of our observations. And these probabilities always sum up to 1. And of course, similar to the regression task, we can run the summary function to get the effects on our responses. But we see that here we get now the effects for each of our 3 responses, so for each species. And also when we plot now this neural network here, we see that on the right side here, we have now 3 output nodes. And each output node here corresponds to 1 species in our dataset. Okay, so one big challenge with these deep neural networks is the convergence. So during the training, we get this plot here on the right side. Here in green, we have this baseline loss. Again, this is just a loss of an intercept-only model. And the idea is that our model should at least outperform this baseline model. Then on the left side, we see the actual loss, the current optimization step. And here we have the epochs. So we don't call it iteration because this epoch means that we have the data set, we have used it once during the training. So actually, the optimization is done via stochastic gradient descent. This means that if we have our neural network, just gonna copy it from my solution here. So if we have our neural network here, if we open the documentation again, we have here this batch size. And here we tell you that the batch size is the number of samples that are used to calculate one or used in one optimization step. So if we have a batch size of 30 and we have 150 observations, actually one epoch consists of 5 optimization steps because it will take 5 optimization steps to go once through our data set. So this is why we call this epoch and not iteration. And we train our neural network using these batches because of several reasons. So first of all, if we have big data, then especially the graphic cards are limited by their memory. So we cannot use all of the data at the same time. So we are always loading only batches of the data. And then we only make predictions for one batch of the data, calculate the error and update our weights. But the other reason is that it was shown that using the stochastic gradient descent, it helps to improve the training of these deep neural networks. So it's actually very crucial for the convergence of our deep neural networks. But the big problem in training these deep neural network is actually the learning rate, because it tells the optimizer how large should be the step of the updates in the optimization. And if the learning rate is too small, we see here is that the actual loss is not falling below the baseline loss. And also, if the learning rate is too high, on the one hand, it could be that the training doesn't start at all because the loss is directly NA, and then the training is interrupted by cito. Or if we check here the documentation again, It's also explained here that it can also happen that the loss during the training doesn't fall below the baseline loss. So the idea is that we have to adjust the learning rate in a way that the training loss falls below the baseline loss. So the baseline loss is a very important indicator for you that something is wrong with the learning rate. So what we want to see is that the loss during the training falls down below the baseline loss. And also, let's run it like this. So this is just to interrupt the training if the loss doesn't fall below the baseline loss. So sometimes what can happen is that you see that the 100 epochs are not enough to train your neural network, and then it could be that you also have to increase the number of epochs. So the idea is that we have to set the learning rate so that our neural network converges quickly, but not too quickly, because if the learning rate is too high, either the loss is very stochastic and there are a lot of jumps during the optimization, and not too large that the optimizer is not able to fall into a local minima. So the learning rate is, because of that, the most important hyperparameter, and often it's better to tune this hyperparameter manually. And the second big challenge with machine learning, and also especially deep learning, is overfitting. So many of the parameters you have seen here in the DNN functions are there to prevent overfitting. And for this, for the overfitting, to demonstrate here the problem, I'm gonna use now this elephant data set, which is available in the ecodata package. So here we have these 19 bioclim variables, and then we have here one column for the presence and absence of our elephant. So overfitting means that our model is very complex on the training data and is able to predict very well on the training data, but is not able to generalize well to new data. So the predictions are very poor for new data. This is kind of the rough definition of overfitting. So what we want to achieve is that we want a model that has the right complexity so that it makes good predictions for new data. And when we fit now our neural network here, so again, we're using this formula syntax, and here I'm using now this point here on the right side of the formula. This just means that all predictors, so all 19 bioclim variables, should be used by citos. Cito are used as a predictor. And then here I'm going to change the loss here now to binomial. And then just to demonstrate that we can change the architecture, I'm going here to use now 2 hidden layers, each with 200 neurons. So when we train our neural network, what is also happening during the optimization is that with the number of epochs, the complexity increases. Yeah, so the longer you train your neural network and the lower the loss will fall, the more complex your neural network will get. The reasons for that are not well understood, but roughly said, this is at least what I think is maybe the a strong hypothesis is that at the beginning you have a very noisy ensemble model, and the more you train it, the more the higher complexity will be, because you will use this deserialization effect of this noisy ensemble. So what we usually do in deep learning is that we turn on a validation loss set, or we will use a validation split of the data during the training to monitor our training. So here on the right side, you would now assume that the training was very good, because the training loss is now very low. But when we turn on now the validation data, so use percent of the data for validation during training, which means that we will split at the beginning, we will split the percent of the data away, and we will use this holdout after each epoch to validate our model. Example here, let's use 30% of the data for validation. And then we will get here on the right side an additional orange curve, which is the loss for the validation data. And what we see here now on the right side is that the validation data, the loss for the validation data is also first decreasing. However, after a certain number of epochs, the loss is increasing again. So in other words, at a certain number of epochs, our model starts to make, the predictions of our model are getting worse. And I would say this threshold is here around 250 epochs. And this is what overfitting, what is happening here. So we see that after a certain number of epochs, the model is getting complexer, getting more complex, and the model starts to overfit to our training data. And this is why it's always important to use this validation data, or this validation split, to monitor our training. So we have now several options to prevent overfitting. First of all, we should use regularization. So in deep learning, we are using, similar to as in statistical models or in machine learning, we can use L1, so lasso, or L2 regularization, rich, which we also use, for example, in Bayesian statistics, on the weights of our neural network. So we have this lambda parameter here, which is the strength of the regularization. And then we have alpha, which is the mixture of L1 and L2. So for example, 80% here means 80% L1 and 20% L2. So this is similar to GLMNet. So if I turn it to 1, we have only L2, and if we have 0, we have only L2. Okay, we can run our model again. So I think, of course, you already see it. It may be better, but it's hard to say. And of course, the best solution would be to use cross-validation to set or to find the best set of these regularization parameters. And I will show you in a second how to do that. I just want to introduce another type of regularization that is specific for deep learning, and this is dropout. Dropout means that a random set of the neurons, so if we visualize our neural network, so during the training, a random set of the neurons are set to 0. This is why it's called dropout. And the dropout rate will then tell you how many, or in percent, how many of the neurons should be set to 0 in each optimization step. And with the neurons, I mean, so take some time to plot all these neurons. I mean the links here in black. So these black lines are the connections, and these are the weights. And with dropout, a certain percent of them are set to 0 randomly during the training. So here I tell cito to set 30% of the neurons randomly to 0 during the training. And in reality, we use all 3 types of regularization when we train these deep neural networks. However, so usually dropout can be set to like 30, 40%. I would say it's a good default. Whereas for the L2 and L1, it's very important to do hyperparameter tuning for them. So also, another thing we usually do is, because the training can take a long time, is that if the validation loss is not decreasing at a certain threshold anymore, after a certain threshold anymore, is that we can tell cito to stop the training at this threshold. And this is what we call early stopping. Stop training when validation loss not decrease anymore. So here, this early stopping argument expects an integer, and this is the number of epochs that should be waited until the training is stopped. Yeah, so here 10 means that we would wait 10 epochs before the training would be stopped.
Max, your
Yeah.
screen has shifted slightly, so we can't see the code. We mainly see the plot right now.
Okay, so just give me a second. Just gonna share it again.
Yep, it's back. Thanks.
Okay, since when?
Um, yes, just where you started talking about the validation loss wasn't decreasing anymore.
Okay, perfect. Okay, so dropout just means, again, it will stop after a certain number of epochs where the validation loss hasn't decreased anymore. So if I remove now here this regularization and remember this first plot where we have seen that the validation loss, I'm not going back now, where the validation loss started to decrease after like 100 epochs, I would expect now that the early stopping should stop the training after like 100 or 150 epochs. Okay, and here you see that it has already stopped after 28 epochs. So maybe 5 epochs is is too low because you still will have some stochasticity in the validation loss. So yeah, you see that this idea or that it's very important to use regularization, but of course, yeah, it's going nowhere if we have to set or to find best values for the regularization on our own. And what we usually do is that we do the hyperparameter tuning in a systematic way under cross-validation. So if we take this model from here, we can tell cito that the lambda parameter should be tuned. So we will use this tune function here. We can set here a lower boundary and an upper boundary. We also can tune this alpha here. And of course, we can also tune the learning rate. And my recommendation would be to tune only these hyperparameters. So in theory, you could also tune here the architecture. However, yeah, it's very hard to tune the architecture, and also it's unclear if there is a rule of thumb for the architecture. So the big companies were fighting for the right architecture now since many years, especially in this image classification tasks. And there are also these auto Keras and auto machine learning frameworks that try to find the best architecture, but the best solution for me is to just not tune it, because the other hyperparameters are much more important. Okay, I'm just gonna copy here this code from the GitHub. So here I will now tune only lambda. And problem with the data. Okay, is this code here? And the default for this hyperparameter tuning is that we will draw 10. I'm going to check the help. So here we have this tuning option. So the default is that we will sample 10 random values for our hyperparameters, and then we will do by default only a 5-fold cross-validation. And after the hyperparameter tuning and a cross-validation, Seed will pick the best set of hyperparameters. So here we see our hyperparameters for the lambda that were tested together with the test loss from the cross-validation. And here we see, for example, that this lambda value of 0.009 has the lowest test loss. So this is our final set of our hyperparameters. And then C2 will train the final model on a full data set using the best set of the hyperparameters. So if we print this model here, we see that C2 has used here this lambda value that was found to have the lowest test loss for the holdouts under the cross-validation. Can also print the cross-validation history. And here we see again the lambdas that were tested by C2 and the test loss from the cross-validation. Yeah, and because this is computationally very expensive, we see it here in the documentation. We can parallelize it on the CPU, but we can also use several GPUs when if they are available. Okay, and with that, I think I've covered the most important functionalities of cito. So the hyperparameter tuning of the learning rate because of the convergence and the regularization for the overfitting. This is very important, especially the learning rate. And we have also some advanced features for some advanced models in cito, but I'm going to switch now back to presentation.
Okay, thank you so much, Max. And
No, I'm not finished yet. It's just give me
oh, I see.
sorry. Yeah. Okay. We have also some new features in cito, but yeah, they're not on CRAN yet, so they are already on the development version on GitHub, and they will come in the next few weeks when I find time to finalize the CRAN update. But one big advantage of these deep learning models is that they can handle complex data. So we have the tabular data sets, right, like this iris data set or this elephant data set. But the real advantage for deep learning is that we can use images or time series, for example, for species identification from camera trap images. And just as quick introduction to these convolutional neural networks, these are the types of neural networks that we use for images. And the idea of these convolutional neural networks is that they have these very small kernels that are running over your image. And in that way, you don't have this fully connected neural network. And we can do that in cito. We can have first to specify or set up the architecture of these CNNs, so we can use pre-trained CNNs. And then we can train again very easily these CNNs. And then we get this also, we can of course visualize the architecture. But again, this is not on CRAN yet. And of course, we also have all these other functionalities that I just have shown for these deep neural networks or these fully connected neural networks. And then even more exciting is this idea that we want to combine different data types. So imagine if you have, for example, remote sensing data, but you have also tabular data, or you have environmental time series data sets. You want to combine these different data types. And we can do that in these so-called multi-model neural networks, where we combine different deep learning architectures. So here, for example, a CNN and a DNN. And we have actually an example that we are also currently preparing. The task is to classify songs of bird species. And we have, on the one hand, we have images of the audios, so the spectrum files. And then we have also additional data, tabular data, for example, telling the model the spatial coordinates, but also the type of the song. So is it an alarm call? Is it a flight call? Or what type of call it is? And in cito, we can combine then these two architectures in this function, which we call MMN. So we have a CNN branch for the images, and then we have a DNN branch for the tabular data set, and then the response is the species. And then again, you see you have the loss function and the device and the optimizer. And it can, here in this example, we see then, for example, it improves the performance over the CNN and the DNN. And we hope that we can get this on CRAN in the upcoming CRAN and the upcoming update, which I hope I can finalize in the coming weeks. And with that, yeah, thank you for your attention. I hope that cito will be helpful. So at least for me, it's very helpful, and especially this interpretation or this idea that we can really get these effects out of these neural networks is very interesting for me, because also have used it to identify kind of complex ecological effects, like in these ecological networks where we want to predict species-species interactions, and there we want to find this trait matching, for example. Yeah, and also, of course, in species distribution models, we're not only interested in making predictions, but also understanding, so what is explaining the distribution of species.
Thank you so much, Max. Let's see. We have a couple questions on the poll everywhere. So first is highly rated. So ecologists are very used to hierarchical models, and many statistical design are based on blocks or cluster sampling. So is this necessary or appropriate in deep learning frameworks? So for example, is the random slope intercept terminology relevant here for the deep learning stuff?
Okay, that's a very good question. And actually, yes, so kind of. So we started to play around with this idea. So we have an option that I haven't shown here yet. So I'm not sure for the person who has asked this question that there's also this idea with this random splines in GAMS. So in MCCV, you can set this random effect on the splines, right? So that you get these random splines. And we are currently implementing something similar in these deep neural networks so that we can, if you have on the right side, you have a kind of variable that is kind of a blocking variable or just kind of a factor. So for example, if you do a multi-species SDM and you have the species on the right side and on the response, you have just the presence and absence. So you have the long format. The idea is that we can tell the deep neural network to kind of identify random splines for the SDM for the species. Yeah. So I would say we are interested and we're working on this, but it's not really coming from the deep learning literature. This is more that we are interested into getting these kind of random effects or these hierarchical structures out of these deep neural networks, because we think this is also a great opportunity for these deep neural networks.
Okay, thank you very much. So the second question is, the audience are wondering if you can speak to the advantage versus disadvantages between these feed-forward networks versus random forest or tree-based methods such as extreme gradient boosting or light gradient boosting method.
Yeah, that's also a good question because random forest, for example, is a great algorithm. It's much easier to fit because you don't have these conversion issues. You don't have so many hyperparameters. In reality, I would say there are only a few fields or applications where there's a real advantage of these deep neural networks. And first of all, if we look at the inductive bias of these algorithms, we have a paper showing that these deep neural networks have a smaller bias in identifying the true effects in the data. And this is related to the problem of collinearity. So if your variables are collinear, the random forest, the inductive bias in the random forest will cause the random forest to do a spillover. So if you have two effects and they are correlated with each other and one has an effect and the other not, then basically the effect will be shared by the random forest. And this is, of course, a problem if you are really interested in identifying the effects that are relevant. And here we found that the deep neural networks have a better ability to disentangle these collinear effects. And the second advantage over these tree-based algorithms is that neural networks are better in identifying interactions between predictors.
Okay, thank you. The third question is about the uncertainty quantification. So the reliable estimate of the 95% confidence interval via bootstrapping would require many or hundreds or thousands of iterations for intervals. So is this computational feasible with this method?
I would say I don't think you need thousands. I mean, the error is, or the variance is of the bootstrap estimate is with square root n falling, right? So I wouldn't say that you really need hundreds of thousands of bootstrapping samples. So it should already stabilize after like 50 bootstraps. But yes, of course, it's computationally expensive, and we're also working on finding an analytical way of calculating these confidence intervals.
Mm.
Because of course, bootstrapping, for example, these convolutional neural networks or these very big architectures is just infeasible. So that's not possible.
Yay, thank you. And the fourth question about how the size of data set. So is there a general rule for how big a data set must be to use the DNN? And how do I check if my data set is too small?
Yeah. Okay, so there's always this misconception that you need big data for deep learning, right? But I would say that the problem of small data is that the hyperparameter tuning is just more challenging, right? So the regularization, of course, with the help of the regularization, you can adjust the complexity to your data. So it even works with small data. And I mean, regularization emerged from a field where we needed models that can deal with data sets where we have more predictors than observations. So I wouldn't say there's really a hard limit for deep learning or for these fully connected neural networks. I think that often there are just practical limitations. So for example, this cross-validation setup. I mean, if you have like, let's say a species distribution data set where you have only, let's say 20 or 40 presences, then if you do a tenfold cross-validation, you will end up with like 5 presences in a test data set, or you don't have enough power anymore. Let's put it this way. And this is what I would say is the practical limitation that really depends on your data set, on your variables. And also if you have certain variables with many levels and you cannot do cross-validation anymore, then it's very hard to do this hyperparameters tuning. And then I would say this data is too small for the neural networks.
Hey, thank you. And then what functionalities would be lost when switching a deep learning workflow from leveraging PyTorch or TensorFlow to cito?
Sorry, which functionality or
Like what if you change from Python-based PyTorch or TensorFlow to the R-based cito, what kind of functionalities will be lost?
uh okay, I mean in general, if you go from PyTorch to Torch for R, I would say almost no functionality anymore because the RStudio team has implemented all functionalities in Torch for R nowadays. So even these new architectures like transformers, so they're already available in Torch for R. So I would say on this side, everything is already there. So but for cito, I would say because cito is a wrapper around Torch for R, of course, it doesn't have the same functionality as Torch for R or PyTorch, right? So because it's a higher front end to Torch for R, and we will never have the same flexibility as Torch for R because actually we wanted to get away from this high flexibility, and we wanted to limit the complexity.
Hey, thank you. And the next question is related with this one. So, given increased use of AI in ecology and the fact that Python is the most often software for such models, do you recommend ecology students learn Python in addition to R?
Um, uh, I would say that if you know R very well, then Python is not so far away. Um, yeah, it's hard to answer this question. So I would say it's always good to also know some Python. Um, but I would say that it's enough to learn one of these two languages, and then I would say that it's kind of easier to switch between the two languages. But I would say that one of the two is enough for the students.
Sounds good. And also the next question is, the audience saw MVP as a loss function for multi-species occupancy models. Have you thought about incorporating MPP or other for multi-species joint abundance models?
Um, yeah, so to give a bit of a background, so this multivariate probit model is only in there because I'm also developing this SGSDM package, which is a package for joint species distribution models, and there we are using PyTorch to do a Monte Carlo approximation of this model, of this likelihood. And I thought it would be nice to have this multivariate probit model also in cito. But I don't think that we will further develop cito in this direction because it should remain a general purpose package. So it should be not a package for a specific ecological task. So what we have started is that we have to develop cito-based packages for specific ecological tasks. For example, we're currently working on cito move, which is using cito for fitting step selection functions for predicting or understanding animal movement. And so if I have time, my plans are also to move this SGSDM package to Torch4R and also build there or implement their other models for multi-species models, including occupancy models.
And the last question is about the interpretability of the AI model. So do the explainable AI functions such as ALE, I think it's accumulated local effects, work with other kinds of model objects besides the DNA fits, the DNN
No,
fits? Yeah.
no, they don't work. So the problem is always that with this XAI stuff, there are packages that you can use for any type of machine learning model. But there you always still have to provide a certain predict function wrapper because the problem is that many implementations of these machine learning and other deep learning algorithms in R, they always have a different interface. And this is why it's very hard to provide or to create one function that or an S3 type of methods for all different machine learning implementations in R. So no, the answer is that it's only working for DNNs from cito.
That makes sense. Okay, thank you so much. And that's all the questions. And thank you again for giving such a great seminar and also all the questions.
Thanks, Max. It was great. Thanks, everyone, for joining us, and we'll see you next month, March 2nd. Bye, all.